Hey, North, Mr. Yurgler here. Now that we've talked about enthalpy and entropy, now we can talk about Gibbs free energy, where we kind of combine the two ideas. We've talked about what makes a reaction favorable. It can be favorable from an enthalpy perspective because systems tend to go from higher energy to lower energy. If we have a system where the reactants are high in potential energy and then they lose energy in the process of the reaction, then that's a favorable reaction. And your delta H is going to be negative, right? Less than 0. So anytime we're losing energy, you could think of that as becoming more stable. The system is going to prefer to go in that direction. From an entropy perspective, we've talked about how if you go from more order to more disorder, if the entropy is increasing because we're dispersing our energy or the matter, then that's going to be a favorable condition as well. So our delta S is going to be higher than 0, right? An increase in entropy. So if we have a decrease in energy or an increase in entropy, then it's going to be what's called a favorable reaction. And here's an example of an increase in entropy, right? If we have a gas trapped and then we open the valve, it's going to automatically, spontaneously fill the other side of the container. So if we have both of these conditions, then the entire reaction overall is going to be what's called thermodynamically favorable, meaning spontaneous. We prefer not to use the term spontaneous because spontaneous, you tend to think of like it happening quickly, but that's not what we mean. We don't mean it's going to happen quickly. The favorability of the reaction has nothing to do with how quickly the reaction goes. It's just that it is going to tend to create products more than stay as reactants. And the equation that connects these two is what's called the Gibbs free energy equation. Delta G is the combination of the change in enthalpy and the change in entropy with temperature thrown in there as well. We can think of free energy as like the amount of energy that's available, like available energy in order to do work. And so this is what you really need to have memorized and have this down. Never make this mistake. A positive delta G is unfavorable and a negative delta G is favorable or spontaneous. If it's 0, then it's essentially neither product favored nor reactant favored. You could say you're at equilibrium when delta G is equal to 0. Thermodynamically unfavorable reactions can happen. So typically what we mean by unfavorable means that the reaction never occurs. It will never occur. But it can be driven by an outside force. So an example is your cell phone battery. It never recharges itself on its own, right? That's a positive delta G situation. You're taking energy and you're inputting it, and you're kind of compacting energy into a smaller space, so to speak, in your battery. That never happens on its own, but it could happen if there's a favorable reaction that's happening that's driving that unfavorable reaction, right? So the production of electricity and the flow of electricity through the wire is dispersing energy. That's a favorable situation. That can be driving an unfavorable situation. Another typical example is cellular respiration. The production of ATP is not a favorable process. It's a positive delta G. ADP does not go to ATP on its own, but it can be driven by a favorable reaction, a negative delta G process. The conversion of sugar plus oxygen to carbon dioxide and water, an example that we've already looked at, is favorable because we're decreasing our energy. Sugar has a much higher potential energy and carbon dioxide and water has a much lower potential energy. So that favorable reaction drives the unfavorable reaction of formation of ATP. And then the ATP is then used in other areas of the body to basically carry out all the bodily functions that your cells do on a daily basis. All right, so let's look at all the possible combinations. We've already looked at this example. If you have a negative delta H, that's an exothermic reaction, and an increase in entropy, that's more dispersal, then it's going to be a favorable reaction, right? That's always going to be favorable. Your delta G is always going to be negative, right? A negative minus a positive is always negative. What about the opposite? If we have an endothermic reaction and a decrease in entropy, a positive minus a negative is basically a positive plus another positive, right? That's going to be a positive delta G. That's never, ever, ever going to be favorable. So what if we have an endothermic reaction, which would normally be unfavorable from an energy perspective, but we also have an increase in entropy, which would normally be favorable? What kind of conditions would make this have a negative delta G? What kind of conditions would make it a favorable reaction overall? We haven't really talked about temperature yet. If the temperature is really large, if this T delta S is much larger than the delta H in absolute value, then you're going to have a positive minus a larger positive, which would then make it a negative. So a situation like this is going to be favorable, but at high temperatures, where your entropy change is more significant. What if they're both negative? So we have an exothermic reaction, which would normally be favorable, but we have a decrease in entropy, so we're getting less disordered. This is going to be favorable at a low temperature because your T delta S is going to be rather insignificant. So you're going to have a negative value minus a negative, so it's positive, but because it's smaller, because you're at a low temperature, it's not enough to make the delta G positive. Okay, so we can think about Gibbs free energy as being unfavorable or favorable. You could also think of that as being reactant favored or product favored, right? And using that terminology kind of brings back memories of equilibrium. Remember that equilibrium is basically a measure of how much product you have relative to how much reactant you have. And so we can actually connect the K value to this. If you have a positive delta G, then that's going to be similar to if you have a K value that's less than 1. Remember that K is never negative, it's always positive, but less than 1 means it's reactant favored. Greater than 1 means that it's product favored. And this is the algebraic relationship between the two. So we have our delta G, and the delta G can be found just like Hess's law. We can sum up all the products and sum up all the reactants and subtract. And then the R is the universal gas constant. That's always going to be 8.31 joules per Kelvin per mole. And then temperature has to be in Kelvin. And then the natural log, ln K, would be natural log of our equilibrium constant. So let's look at a few quick examples. If we have this reaction, the K value is really small, product favored or reactant favored. That would be reactant favored because we have very little products, right, which makes it small. And if it's very reactant favored, then that would make sense that it would be a positive delta G because it's not a very favorable reaction. It tends to stay as reactants. It doesn't go to products. An opposite example would be this reaction where we have a large K value, and then it would make sense for it to be a negative delta G. So you need to be able to identify if a reaction is going to be favorable or not, and you need to be able to make the connection and see the relationship between the K value in equilibrium and the delta G value in Gibbs free energy. Once we start working through a few examples of this, it'll make a lot more sense. It'll be pretty straightforward. All right, this is Mr. Igler signing out.